Next step is to select a trial binder content on the basis of past experience or to make sure to meet the requirement of minimum binder film index of 7.5 micrometer or greater. The binder film index is a measure of the average binder film on the aggregate particles, excluding any binder which might be absorbed by the aggregate. This allows the mix to have adequate durability and fatigue resistance. Normally, the binder film index gives the minimum binder content, and the trial binder content will normally be 0.5% higher than this. By using the trial bitumen content and the trial 1 plus and minus 0.5% and 1%, we're able to get a range of bitumen contents. Once the trial binder content is chosen, we start to mix and then condition and compact the asphalt mix in step 5. We need to ensure the sample prepared in the lab have properties as close as possible to asphalt placed in the road, and this is an important aim of asphalt mix design procedure. As I discussed before, the class 320 bitumen is commonly used in asphalt for medium and heavily trafficked mixes, so we will choose it for mixing. The mixing is conducted for a range of bitumen contents and normally in between 4% and 6%. The aggregate and binder are heated in an oven and mixed at 150 degrees. The mix is then transferred to an oven and conditioned under 150 degrees for 1 hour. It simulates the hardening of the binder during manufacture, placing of the mix, and initial service period. In such case, the prepared sample could reflect the real behavior of the filled pavement. For the compaction of the sample, the gyratory compactor is used to compact the samples for the required number of cycles. The compactor could produce 100 millimeter and 150 millimeter diameter cylindrical asphalt samples of specified density. The applied shear force to the asphalt mix is similar to that from the roller during the construction of the road. During compaction, the mold is rotated relative to its vertical axis shown here through a constant gyration angle during the compaction process. So this is the gyratory or gyration angle here. So the vertical compressive pressure is applied to the asphalt sample within the mold. The produced samples have mixed characteristics very close to those found in the filled pavement. This is the data sheet for gyratory compaction tests. This enables a selection of different compaction levels to match service conditions and simulation of long-term heavy traffic by compaction to refusal density. The refusal density is also the final density of the sample. Step 6 is to determine the volumetric properties to select design bitumen content. Let's have a look at the volumetric relationship. In the diagram, the HMA stands for hot mix asphalt. The bigger particles are the aggregate. Some of the asphalt are absorbed into the aggregate. The VMA or voids in the mineral aggregate are occupied by the air voids and effective asphalt binder. From the right volume diagram, we can also see that the asphalt binder is composed of the effective asphalt binder and absorbed asphalt binder. If the relationship is expressed in terms of mass or volume, here's how the composition looks like. If we look at mass, normally the air voids have no weight. The bundle is expressed as capital B, and BE stands for the effective bundle, and small b for absorbed bundle. From volume point of view, AV is the volume of air voids, and VB is the effective volume of the bitumen. The sum of them is called VMA, the voids in mineral aggregate. Typical values of VMA in dense mixes can be 13% to 20%, depending on the nominal size of the mix. Finally, Vg is the volume of the aggregate, including the absorbed bundle. I would strongly suggest you to pay more attention to these definitions and relationships, as you'll need to use them for some calculations. So based on previous figure, we have the following useful volumetric relationships for air void content AV, voids in mineral aggregate VMA, and voids filled with bundle VFB. Among these formulas, the rho max is the maximum density of asphalt in tons per cubic meter. The rho bulk is the bulk density of asphalt in tons per cubic meter. And capital B is the proportion by mass of bundle in total mix. Rho B is the density of bundle in tons per cubic meter. And finally, rho A is the bulk density of the combined mineral aggregate in tons per cubic meter. This is the follow-up of previous slide. The bulk density of the combined mineral aggregates could be calculated using this formula. The physical meaning of each symbol is shown below. The BE is the proportion by mass of the effective bundle as percentage, which can be obtained from the following equation. The small b is the proportion by mass of the bundle absorbed as percentage. It could be calculated from the bottom equation. After you conduct the lab testing, you should be able to obtain the measured values for datasheet C.1 and D.1. The maximum density of asphalt or rho max could be obtained by the combination of the table and the formula below. We are at the M1 to M5 are the testing measurements. Similarly, the bulk density of asphalt could be calculated based on the datasheet D1 and the formula below. We are M1 to M3 are the testing measurements in the table, and rho W is the density of water in terms of grams per cubic centimeter. After we conducted tests on the samples of 5 different bitumen content, we are able to get the relationship plot of this air voids density and VMA, or voids in mineral aggregate of the compacted samples and bitumen content. They could be used to evaluate whether the mix meets any required specifications. If the mix has the required air void content, then the bundle content could be determined from the plot. For example, if the air void of 5% is required, then according to the first figure, the design bitumen content is chosen as 4.8%. Also, we could check the sensitivity of the asphalt mix in terms of these parameters to bundle content from these figures. For example, if the bitumen content was increased from 4.5% to 5%, how the air voids, the density, and VMA change accordingly.